Let's take a look at how we could use the sketch of a function or the graph of a function to sketch its derivative. Here on the right, we have the graph of a discontinuous function. Notice it has a couple of jump discontinuities. And what we want to do is below sketch the graph of the derivative of this function. So I've zoomed in a little bit here to help us focus on what is happening with our original function. So we'll go ahead and focus on the upper graph and start thinking about slopes of tangent lines. So recall that one interpretation of the derivative is that it is the slope of the tangent line to the curve. So we'll start over here near the y-axis and think about what the slopes of tangent lines to the curves are. So if you'll notice here we have a positive slope, a rather steep slope, and as I move along my curve, notice that that slope is remaining positive. However, it is decreasing. It is becoming more and more shallow. So again, my slope is positive, just not as large of a positive number as it was before. Until we reach the point here at the top of this appears to be maybe a semicircle or something similar, where my slope is actually 0. So at that point, I know that the derivative is equal to 0. So that's going to help me with drawing my graph of my derivative. Is I'm going to come down here to my axes for my derivative, and I know that my derivative is 0. That means the derivative function is going to cross the x-axis about at that point. So now let's sketch in what we think might be happening between the y-axis and where our derivative crosses the x-axis. And we did note that our derivative, our slope of our tangent line, was rather positive and it started decreasing. So the derivative function, let's assume that it's a fairly large positive number. So let's assume that maybe this represents the slope at that initial point. And then now my slopes are becoming less and less positive. The tangent line is becoming more and more shallow and approaching a slope of 0. So our derivative could look maybe something like this. Now we continue to work our way along the graph of our function, and we notice that after our slopes, the slope of a tangent line is 0, then we see our slopes becoming negative, and indeed more and more negative, increasingly negative, until we reach this point, this sharp corner. So that means that for our derivative, once we pass through the x-axis, our derivative will be negative, and it becomes more and more negative until we reach that point on the x-axis. So it's going to look maybe something like. And so now we come back up to our original function, and we look at this point where the graph has touched the x-axis. And moving to the right, it appears we have a line segment. That means it has a constant rate of change. It has a tangent line, but that tangent line ends up, in essence, lying along the line segment. So that's going to be constant, so that's going to end up being a horizontal line. And we're just going to estimate and say that our slope of our tangent line here is roughly at about this height. And that should be a horizontal line. Now, it doesn't exist at the left endpoint, nor does it exist at the right endpoint. Same here for the previous component. Okay, so let's make sure that I made that align with where this discontinuity is for our original function. So following this down, it looks like I might have made that, yes, a little bit long. So we will shorten that up a little bit. And so it will look like that. Moving along, now our graph of our function jumps down below the x-axis. Again, we have another line segment whose slope is positive, and it actually looks to be about parallel with our previous line segment, which means the slope of the tangent line for both of those line segments is going to be about identical. So let me go ahead and demark where we're considering this derivative. And so we have, in essence, the same slope. So we're going to have a horizontal line as our tangent, because the slope of this segment is constant. And because that slope is constant, the slope of the tangent line is always the same. So we end up with our slope of our tangent line being a horizontal line. Now notice we do have a jump discontinuity here, so we will be putting an open circle at the end of that portion of the derivative. Now moving on, we see we have a segment of our function that is a horizontal line. And this horizontal line, let's consider the slope of its tangent line. Because it is a line segment, our tangent line does end up falling on top of that line segment. And it is a horizontal line segment, which means the slope of that is 0. So we're going to have a slope of 0 in this region, or a derivative of 0 in this region. And let's go ahead and mark that interval. On the left, we will have an open circle. And on the right, we will have an open circle because of the existence of a corner here. If I look at that corner, I do not have a unique tangent line, meaning only one tangent line. So for example, at this corner here, I could have a horizontal tangent line. I could have a tangent line that looks like this. I could have another tangent line in here. There's actually an infinite number of tangent lines that I could have at this corner. And because that tangent line is not unique, the derivative does not exist there. And now it looks like we have one final segment that we need to look at. And as I look at that segment, I see again I do have a line segment. And as I consider the tangent line to that line segment, again that tangent line will lie on top of the line segment. And notice that that is decreasing, or the slope of that tangent line is negative. So that means my derivative is negative. And so we'll estimate, and based on what I estimated for the positive slopes, I'm going to estimate that this negative slope, this negative derivative, is right about there. Now, On the left endpoint, as we discussed, the derivative does not exist. And notice that the function fails to continue after that point. So the limit does not exist on both sides of that point for our derivative. So our derivative will have an open endpoint on that right end of the line segment. So now what we have is a sketch of the graph of the derivative of our function. Notice we have this curve that passes through the x-axis. These two slanted line segments that have positive slope have created this horizontal component of the derivative. This horizontal component of our function has created an interval on the x-axis where the derivative is 0. And then this decreasing component of the derivative has created a portion of our derivative, this decreasing portion of our function has created a horizontal line segment with negative y value. I hope this helps.